Welcome to Another Explainer. If you've ever stared at a mathematical glossary and felt like you were trying to read some ancient, indecipherable language, trust me, you are not alone. A to Z lists of terms, from absolute value all the way to velocity, they can feel incredibly dry and totally disconnected. But today, we're going to flip the script. We are taking the standard additional mathematics glossary and restructuring the whole thing into an interconnected, logical framework. We're turning a simple list of words into a vibrant, living map of mathematical concepts. And hey, I want to reassure you right out of the gate, we are absolutely not just going to sit here reading a dictionary together. No way. Instead, we're taking a guided tour through 5 specific mathematical neighborhoods. First up, algebra and polynomials. Then, we'll shift gears into the rules of functions, step on up to sequences and series, dive deep into the core of calculus, and finally, we'll land right in the physical world with vectors and kinematics. It's all about building your conceptual ladder one solid step at a time. Section 1. Algebra and polynomials. Okay, let's break down this matrix. A polynomial is really just an expression where your terms are positive integer powers of a variable. But here's the trick. Rather than trying to memorize them all randomly, if you organize them by their highest power, which mathematicians call their order, it creates this immediate, super easy to remember hierarchy. So a linear equation has a highest power of 1, and it graphs as a totally straight line. Step that up to an order of 2, and boom, you've got a quadratic. An order of 3 is a cubic, 4 is a quartic, and 5 is a quintic. Just by counting up to that highest power, you instantly know the name and the fundamental shape of the math you're actually dealing with. It's kind of brilliant. Now, once we have our polynomials, how do we actually break them apart? Enter the factor theorem. I don't want you to just look at this as some boring rule you have to memorize. Think of it as an unbreakable law of mathematics. It elegantly connects factors to roots. It basically tells us that if you plug a specific value into your polynomial and it equals exactly 0, well, you've just found a root. You found the exact spot where your curve crosses the x-axis. It is a perfect logical lock-and-key mechanism. Building right on top of that foundation, we get the remainder theorem. Think of this as the factor theorem's broader, incredibly useful older sibling. If plugging a number into your function doesn't give you 0, whatever number it does give you is exactly the remainder you would get if you did all that long, tedious algebraic division. It acts as a ridiculously powerful shortcut, literally saving you massive amounts of calculation time. Before we completely leave the world of algebra, we really need to highlight a crucial philosophical difference in math. I'm talking about identity versus solution. When you find a solution, you're finding specific, hidden values that make an equation true. Kind of like finding the exact roots of a quadratic equation. But an identity? An identity is a universal truth. It is true for absolutely all values of the variable. You solve for a solution, but you rely on an identity. Section 2. The rules of functions. What's truly fascinating here is how we frame the actual journey of a number. Your domain is your starting point. It's the complete set of all possible inputs you are mathematically allowed to feed into your function. The range, which you might also hear called the image set, is the ultimate destination. It is every single possible output value that the function can spit back out at you. Really understanding a function just means knowing exactly where you're allowed to start and exactly where you might end up. Now, if a function takes you from the domain over to the range, the inverse function is basically your mathematical undo button. It completely reverses the effect of the original function. It grabs your output and drags it right back to the original input. And when we want to get really industrious, we start using composition functions. Picture this as a high-speed mathematical assembly line. You feed a number into the first function, and the output it generates doesn't just sit there. No, it immediately drops right onto the conveyor belt and becomes the input for the very next function. It creates a seamless, ongoing chain of mathematical operations. Section 3. Sequences and series. When we're comparing the two main flavors of sequences, I want you to think about their pacing. An arithmetic sequence steps forward at this nice, steady pace, using addition or subtraction. It changes by a fixed amount every time, which we call the common difference. A geometric sequence, on the other hand, leaps forward through multiplication. Every single term gets multiplied by a fixed number, known as the common ratio. So basically, arithmetic walks, but geometric runs. When we actually start looking at geometric series, where we're adding all these leaping numbers together, we run into 2 totally distinct behaviors. A convergent series has terms that get progressively smaller and smaller. Think of it like zooming in closer and closer until you hit a single finite pinpoint. But a divergent series,
Its terms become progressively larger, essentially exploding outward into infinity. There's no pinpointing that one.
To wrap up this particular neighborhood, let's quickly connect the jargon. While a sequence is simply your ordered list of numbers, a series is the actual sum of those terms. The process of doing that math and adding them up, that is summation. And an infinite sequence is exactly what it sounds like, a sequence with an endless number of terms. The really amazing thing here is that mathematicians have developed incredibly clean, precise equations to bundle up and sum these infinite, ongoing lists. It's mind-blowing when you really think about it. Section 4. The core of calculus. Calculus presents us with the ultimate mathematical duel. On one side, you have differentiation. This is the process of slicing things apart to find the exact rate of change at a specific microscopic moment. That's your gradient function. On the exact opposite side, you have integration. That's the process of taking that rate of change and putting all those tiny slices back together to find the total overall value at the end of an interval. They are literally two sides of the exact same mathematical coin. Now, when you're slicing equations apart with differentiation, the basic rules sometimes just aren't enough to get the job done. That is exactly why you need an essential toolkit. The chain rule handles a function that's wrapped up inside another function. The product rule is what you deploy when two functions are being multiplied together. And the quotient rule, that's your go-to when you have a ratio of two differentiable functions. Master those three specific rules, and honestly, you can differentiate almost anything. So the really crucial point here is how differentiation helps us literally see a curve without ever actually having to graph it. A stationary point is a spot where the gradient is exactly 0. The curve goes perfectly flat for just a microsecond. A turning point is a specific type of stationary point where the curve flips from increasing to decreasing or vice versa. Think of it like the absolute peak or the lowest valley on a roller coaster ride. And a point of inflection is where the curve physically flexes, changing its entire shape from concave up to concave down. When we flip the script over to integration, we're basically looking at two main types. A definite integral has strict non-negotiable boundaries or limits. It evaluates the total value between point A and point B, handing you a specific, solid number. An indefinite integral, though, has absolutely no limits. It is totally unbounded, resulting in a general algebraic solution that always includes that famous arbitrary constant, plus c. Never forget the plus c. Section 5. Vectors and kinematics. The fundamental difference we're looking at here is incredibly practical for the real world. A scalar is a quantity that has magnitude, but absolutely zero direction. Think of speed. You are driving 50 miles per hour, but we have absolutely no idea where you're actually going. A vector, however, gives you both magnitude and direction. It's 50 miles per hour, due north. Adding that specific piece of directional information completely changes everything about how we calculate and predict movement. And this brilliantly illustrates how every single thing we've talked about today comes together to form the kinematics chain. You start with displacement, which is just your distance from the starting line. You differentiate that and you get velocity, the exact rate of change of your displacement. You differentiate your velocity and boom, you get acceleration, how quickly your speed is actually changing. This is calculus perfectly describing the real, physical world in real time. We've just taken a massive, intimidating glossary and completely revealed the hidden architecture running right beneath it. By grouping these concepts together, from simple polynomials all the way up to complex kinematics, we can clearly see that advanced math isn't just a random list of jargon you have to blindly memorize. It's a deeply connected, logical language just waiting to be spoken. So I want to leave you with a question to chew on. How will recognizing these hidden connections completely change the way you tackle your very next complex math problem? Thanks so much for joining me on this explainer, and remember, keep looking for the patterns.